You breathe about 10,000 times in a day, but do you know how your rib cage moves to make all this possible? Not so sure, right? It's okay, we're going to figure out together. What's up, ladies and gentlemen? Welcome back to Neurosketch with Dr. Kenny. But if this is the first time you've seen this channel, don't forget to subscribe. Today we're talking about the mechanics of respiration, the movement of the thoracic cage. Alright, folks, let's dive right in. You probably know already that lungs are elastic in nature, that they expand to inhale and recoil to exhale. They are in constant movement, but there is small to no space between the lungs and the thoracic wall. The lungs are found within the chest cavity, which is now thoracic cavity, and the space between the lungs and thoracic cavity is very small to no space. This means that for the lung to expand and recoil, we also need to have the movement of the thoracic cage. The thoracic cage and the lungs, they should be in constant movement to enable respiration, like breathing in and breathing out. But let's remind ourselves about the Boyle's law. According to Boyle's law, the pressure is inversely proportional to volume. This means that whenever the pressure goes up, the volume goes down, and the other way around is true. When the volume goes up, the pressure goes down. Is it really significant? Is it really important to our case? Yes, it is, because according to Boyle's law, when the volume goes up, the pressure should go down. So if we have increase in volume of the thoracic cavity, the volume of the thoracic cavity or interthoracic volume, the interthoracic pressure goes down. So why is it significant? It is important because the interthoracic pressure now becomes lower than atmospheric pressure, and that what happens, we create a pressure gradient, a difference in the pressure between the atmospheric pressure and the intrathoracic pressure. Some people would refer this pressure as a negative pressure, like because it goes down below the atmospheric pressure, it creates a negative pressure gradient, and so the pressure goes in, the air goes in as in inhalation. So whenever you have increase in the thoracic cavity, increase in the volume of the thoracic cavity, you will have inspiration, because pressure will be lower than atmospheric pressure, and that's according to Boyle's law. That's how inspiration is achieved. And then quite the opposite happens in expiration, that when the thoracic cavity, the volume of the thoracic cavity goes down, interthoracic pressure builds up, and the result is the atmospheric pressure becomes lower than intrathoracic pressure, or the interthoracic pressure becomes higher than atmospheric pressure, creating a pressure gradient in such a way that air will move from inside to outside, and that process is known as expiration or exhalation. That's according to Boyle's law. In summary, whenever you have increase in the thoracic volume, you have inspiration, and whenever you have decrease in the thoracic volume, you have expiration. But why is this volume? What is this volume we're talking about? You can assume the thoracic cage to behave a little bit like a cylinder, and you remember the area of the volume of the cylinder equals to area times the height. What is the area? The area here is circular, and so we have the pi r square, pi times radius square times height, giving the volume of the thoracic cavity. The volume of the thoracic cavity. But the thoracic cavity is not the perfect cylinder. It behaves a little bit like elliptical cylinder, meaning that got two. Its cross section is a little bit like oval. It's not circular like in a perfect cylinder. It's a little bit like oval, and so it has got different diameters. This diameter is not the same as this one. So when you're going to calculate the volume of this elliptical cylinder, you will take this volume, this radius times this radius times the height. This brings us into very important discussion about the diameters. The diameters are the diameters of the thoracic cavity. When you take a cross-section and thoracic cavity, you see something like this, and you see it is not circular, it's a little bit like oval, meaning it has got this diameter, and this diameter is called anterior posterior diameter, because it runs from anterior plane into the anterior posterior plane, and then also have the transverse diameter, the transverse diameter, which is running from the sides of the thoracic cavity, but it has also got a height, and the height of the thoracic cage, it behaves as it is considered the vertical diameter. The vertical diameter is what would be considered as height of it would be considered the height of the cylinder. So in this way, the volume will be calculated a little bit. It's not a perfect. This is not a correct mathematics, but it somehow behaves in a similar fashion. What is the take home here? That the volume of the thoracic cavity, it is a function of diameter, meaning that whenever you're going to change the diameter of the thoracic cavity, any of the diameter, whether the anterior posterior diameter, the transverse diameter, or the height, which is the vertical diameter, we for sure have a change in the volume of the thoracic cavity. And we know if the volume of the thoracic cavity changes, the pressure will change, and then it will determine whether to have inspiration or expiration, depending on the pressure gradient, right? So let's see each volume, how each volume affects the mechanics of the respiration, starting with the vertical height, which is also could be considered as the height of the thoracic cavity. We have the diaphragm here, and the diaphragm, we discussed about the diaphragm. It is a dome shaped. We have a discussion with diaphragm somewhere else. I'm going to put the ring downside, but this is the diaphragm, and it behaves a little bit like a dome. It's a dome shaped, and when the diaphragm, which is very, very important here, when the diaphragm contracts, it pulls, it goes downward, it flattens, goes downward, it flattens in a similar way as you're opening an umbrella. In this way, and this increases if it goes down, it flattens, goes down, it increases the height of the thoracic cavity, which the height of the thoracic cage or cavity, which corresponds to the vertical diameter. And so if you have the vertical diameter increased, means you have inspiration. Why inspiration? Because the intrathoracic pressure becomes lower than atmospheric pressure, and then air goes in. Quite the opposite happens when the diaphragm now relaxes. It resumes, it goes back to its original shape, which is a dome shape, in a similar fashion as how you are, closing an umbrella, incomplete closing of an umbrella. This will result into decrease in the vertical height, as you can see here, changes from this one to this one, because the vertical height goes down, the intrathoracic pressure goes higher, and then higher than atmospheric pressure, and then air goes down. So relaxation of the diaphragm will result into exhalation in the principle that we've seen. So the take home here is that the diaphragm is the chief inspiratory muscle. Because its action, when it contracts, it pulls, it flattens and becomes increasing the intrathoracic, the vertical height or the vertical diameter of the thoracic cavity, resulting into inspiration. Articular surfaces of the tubercles of the upper 6 ribs are convex, which fit into the concavities of the corresponding transverse costal facet, forming an hinge joint. So we have a hinge joint between the neck of the rib, or the tubercle of the rib, and the transverse and the corresponding transverse process. And remember, the characteristic of the hinge joint allows movement in one direction, and that movement is rotational movement. So we'll have a rotational movement here, who the center of axis, the axis of rotation, is through the tubercle, the neck of the rib. Assume this is the rib. Let me show you here. So assume this is a rib. This is the rib. This is the neck of the rib, the tubercle on the neck of the rib, and this is the anterior portion of the rib. So this joint is formed between the concavity of the transverse process and the convex surface of the tubercle. It allows movement in this direction, and this is movement that is allowed. So it moves in this direction. This part here is rotating, but the movement is observed on the body of the rib, in this fashion. So because of that, this movement is called, because it moves in that fashion, this movement it resembles a pump handle movement, just in a similar fashion on how the pump handle moves. Because the pump handle, the axis of rotation of the pump handle is here, but the rotation is happening here, but the movement is grossly seen on the handle it goes. That's how the upper 6 ribs move, and that we call the pump handle movement. It results into elevation of the sternum, and the elevation, if the sternum is elevated, a little bit elevated, you can see the anterior posterior diameter is changing. It's not the same so it was here. The anterior posterior diameter was here, but now due to this pump handle movement, the diameter is increasing. Look at it. Look at this one. We had the anterior posterior diameter which was this wide, but now it this wider. It's even wider. This is a superior view from above. You can see the diameter was here, but now it's here. So the anterior posterior diameter is increased in a pump handle movement, which is very important. It's attributed by the upper 6 ribs. The lower ribs, especially rib number 7 to rib number 12, they are forming the plane joint. They are forming a plane joint. The above one, it was the hinge joint, but this one is the plane joint. The characteristic of a plane joint, it allows grinding movement. But the grinding here is happening in a way that when these ribs now are moving, they are grinding, moving superior, a little bit superior, but on the lateral surface. So they're moving superior, but on the lateral surface, and this gives an impression. Of the bucket handle movement. The bucket handle movement. Why? Because this is the bucket handle. The ends of the bucket handle are fixed. Yeah? The ends. This one is fixed here, and the other one is fixed there. But what moves is the body, or the body of the handle that is moving. This is also the same to the ribs, because the sternal end and the vertebral end and the sternal end are all fixed, and it's only the lateral part of the rib cage that is moving. The lateral part of the rib that is moving and gives an impression of a bucket end, because the joint here is a planar joint, is a plane joint. It's not the same as that one. So this results into increase in the transverse diameter. Transverse. Look, it was here. So it was here. The diameter was here. But now, because of this bucket handle movement, the diameter goes this wide, and so we have an increase in the transverse diameter. In short, all this movement will result in the same mechanism, and that is increasing the thoracic volume. The diaphragm will contract to increase the vertical diameter, but the pump handle will increase the anterior posterior diameter. The bucket handle will increase the transverse diameter, and the outcome is we have increased the volume of the thoracic cage, meaning the intrathoracic pressure goes down and air goes in as an inspiration. All this mechanism will result into inspiration. On the other hand, expiration is mainly a passive process, meaning does not consume that amount of energy. Why? Because it is the recoil of all, it is restoration of this mechanism that will result into expiration. What do I mean here? For example, the diaphragm now will have to go back, to relax, to go back. So we have a flattened diaphragm which will go back into the normal dome shaped, and it will result into decrease in the vertical height, meaning air goes out. Same applies. We had the elevation of the rib cage by the pump handle and the bucket handle, but its recoil of those mechanisms result into decrease in the volume of the thoracic cage, meaning the pressure now builds up and then air goes out in the process known as expiration. So expiration is mainly passive process, but we also see there are some muscles that are contracting to bring this expiration, but mainly it is it is a passive process as compared to inspiration. At some point in a clinical exam, you'll be asked to name accessory muscles of respiration, and the students always struggle to name muscles of respiration. But today I'm going to give you a simple and easy rule to remember. Any muscle that will result into changing the volume of the thoracic cavity, it will be considered a muscle of respiration. But the difference will be some certain muscles will be considered the main muscles of respiration, and the rest will be considered accessory muscles or auxiliary muscles of respiration. But the muscles of respiration can also be divided in two groups: the inspiratory muscles and expiratory muscles. But in the inspiratory muscles, we have the main muscles of inspiration, which is the diaphragm, as we've discussed, and the external intercostal that we haven't discussed yet. Don't worry. And expiratory muscles will have the innermost, the internal intercostal, innermost intercostal, and the transverse intercostal muscles. Don't worry about the muscles that we haven't discussed. Just focus on the muscles that we already discussed, because as you will be moving will be discussed each muscle in turn in later videos. All right, so let's now discuss the accessory muscles of inspiration, which is the main target in a clinical questions, because they ask like a patient is breathing with using accessory muscles of respiration. Okay, what are these accessory muscles of respiration? Number one, inspiratory accessory inspiratory muscle. The main named is sternocleidomastoid. We haven't discussed the sternocleidomastoid. Don't worry and don't attempt to memorize this because we discussed them later, but the idea is the sternocleidomastoid muscle will a little bit elevate the sternum, and so it gives a little bit of that pump handle movement. Don't worry about it. But we have the scalene muscles. We have discussed the scalene muscles, and we have seen they attach into the first and the second ribs. They are coming from the neck into the ribs, so when they contract, they pull the ribs up, and they result into increasing interthoracic volume. We have the pectoralis major and the pectoralis minor. We've already discussed the pectoralis major and minor, but something that I want you to note, I told you like when the muscle contracts, it pulls insertion toward the origin, right? But we can also have the reverse muscle action that we haven't mentioned, but we can have a reverse muscle action in such a way that the insertion acts as a stationary bone, and then the origin is pulled toward the insertion. This is called the reverse muscle action. For example, the pectoralis minor muscle is coming from the ribs and they insert into the clavicle, so inserting to the scapula. So in the reverse muscle action, the scapula acts as the stationary bone, and then the ribs are pulled toward the scapula, and so it results into elevation of the ribs. Elevation of the rib will result into increased interthoracic volume, which acts as inspiratory muscles. But we have subclavius muscle also is coming from the ribs. It pulls the ribs toward the first rib toward the clavicle, increases the vertical the diameter. But also serratus anterior. Serratus anterior is coming from the upper 8 ribs. It inserts into the scapula, but in a reverse muscle action, it can pull the ribs toward the scapula, and it results into increasing the thoracic volume. All right, the serratus posterior superior, also the muscles of the back, and they result into elevation of the upper 4 ribs, but the serratus posterior inferior will depress the lower ribs, and so it gives impression of the recoiling back, resulting into expiration. So these are the expiratory muscle. The subcostalis works in a similar fashion as the serratus posterior inferior, but we also have the abdominal muscles. Don't concentrate on the muscles that we haven't discussed yet. As we'll be discussing the muscles, they will become evident. Okay, so we have the abdominal muscles of those of anterior abdominal wall, for example, the external oblique muscle, the rectus abdominis. Of this muscle, rectus abdominis and external oblique muscle, they will result into pushing the diaphragm. So they are increasing intra-abdominal pressure. They are pushing the diaphragm towards the thoracic cage, and so they are decreasing the volume, the vertical diameter of the thoracic cavity. Okay, they result into expiration. But we also have the muscles like quadratus lumborum. We haven't discussed yet. Don't worry about it. We also have the latissimus musculus. So the latissimus musculus can swing between the inspiratory and the expiratory, but its main action is still debatable. It's not well understood. The action of latissimus dorsi include respiratory movement. Alright folks, this is what I had for you today. If you have enjoyed this discussion, don't forget to like and share this video. But if you have a question, additional comment, put your thoughts in the comment section. I read every comment. But I have an Instagram and a TikTok account. Don't forget to swing there. I regularly post useful information there. Okay, it was nice to have this discussion with you. See you very soon.